Hi, so this is the Applied Deep Learning course class project presentation. My name is Xu Yang and my project partner is Kunyan Han. We have the outline divided into these four parts: introduction and motivation, data generation, model architecture, finally the evaluation and results. So first of all, uh, we basically did the class project of detecting cancer in gigapixel pathology images. And the main motivation for this project is that the visual inspection of the pathology images can be very tedious and error-prone since it involves a huge amount of data to examine. So our goal or aim is to develop a tool to assist physicians in this process of detecting cancer. We first talk about the data generation process. We first calculate the top left coordinates of the patches in L0 slide. So L0 is the greatest magnification level. Then we raise the mask of L0 to generate the label for each 128 times 128 patch of interest. We label the patch as tumor if any single pixel in that patch has the label of tumor. Else, we label the patch as normal. The below code also illustrates this idea. Then we generate the image patches. We first map the L0 coordinates to Lx, which is lower magnifications. We ensure that these coordinates correspond to the exactly same center. Then we read the slide in Lx and generate patches of size 299 times 299, remove background, then generate the unbiased dataset by randomly choosing tumor or normal patches. So for our model, uh, the input shape is batch size 299, 299, then 3 is the number of channels of the RGB images. And we want a binary classifier predicting tumor or normal images. So we firstly try to use the basic convolutional neural network that we designed and only got the randomly guessing accuracy. Then we use the transfer learning, which is using the Inception version 3 model pre-trained on the ImageNet dataset, got the accuracy over 60%, but that is not satisfiable because the base is non-trainable. So we want to make the base trainable, but in order to reduce the parameters, we reduce the number of channels by 0.1 for each convolutional layer. And we got the below model. We use this model to choose our main level of magnification, which is our main input. And we tried L1 to L4. As we can see from this slide, L2 has the greatest performance. It has a very good accuracy, precision recall, and also its heat map is tidy and also correct. So we consider L2, we consider L2 to be great. We have the confusion methods, which is the computing methods of the L2 model on tumor 091, and it looks perfect. So we further improved our model to incorporate multiple magnification levels. Specifically speaking, we are accepting L2 and L3 patches as input, and the model is listed below. We trained our model on 8 slides and evaluated them on 3 slides: 091, 075, 084, and the heat map is shown here and it looks perfect. We also have the numeric values of accuracy, precision, and recall. Thank you for your listening. So here I'm going to quickly walk through the code base of our project. The first notebook is data generation, and we first import the necessary packages here. mount the Google Drive in the Colab file repository, set up the passes and parameters, and the first thing here is to generate the coordinates and the labels for the patches. So we have the race slide, which is defined in the start code, and we have the coordinate origin, which generate a list of coordinates of top left coordinates in the L0 slide, and we check if the patch is tumor by checking if any single pixel in the patch has the label of tumor. Then we finally generate the labels and the labels for the patches in the slide. Then we generate the image patches. We did some pre-processing like background removing, and also we get the patches by using the reslide function here. Then we generate the images, and we have integrated these two parts to have this end-to-end generation. We just need to provide a slide name list. This is the whole slide name list, and you can use the subset of them to generate the data you want. We have levels 2 and levels rated here, and this is the data generation part. So this is the model notebook, and at README specifies this notebook. The model is trained on multiple slides at level 2 magnification with tumor normal ratio 1:1 in the training set, and we test on selected several slides. And the setup just imports necessary packages here and mount the drive here. Then we get the data generation. We combine the A slides data into X and Y. Then we use train test splitting to get train test dataset. And we define our model here. We first import the in section, and we use this code to to reduce the number of parameters by reducing the number of channels of each convolution layer by 10 by 0.1, and we have the model here trained on the training set for like 10 epochs, and we have the validation accuracy increasing like this. The figure is listed here is very beautiful, and we can save our model here and also load our model. So we need to use our model for the prediction. So we have the reslide function and also some the pre-processing code to get the patches in the slide. And here is the predict slide function, which basically raise the patches of the slide and integrate like 32 patches into a batch, then getting the result by using model.predict, and we can return the prediction matrix here. So here is an example of predicting slide tumor 084, and we can save the produced heat map here. Below is the heat maps generated here, and this is the basic heat map 091, and we have load code to stack the heat map with the original slide image as shown here, and we have also 075 and 084. So this is the model that incorporates level 2 and level 3 patches together to do the prediction, and it is mostly similar to the single level model, and we can see the importing here, mounting here, and also data generation. Okay, so for the data generation, we have x1 and x2, which is basically from different level of magnifications, level 2 and level 3. and we can have this extreme 1 and extreme 2 here, which we will use later. And we have our model defined here. We have inception 1, inception 3. Both reduced the number of parameters by reducing the number of channels in the convolutional layers. And we use the functional API of keyroots to produce the model. We have input 1, input 2, x1, x2, and concatenate x1, x2. Do the basic processing here, reaching the output and getting our model. So here is our model summary. And model compilation, model fitting for 10 epochs, and also give like over 99% accuracy on validation dataset. We have our training curve here, and also all those loading model prediction. Oh, it is worth noting that we also modified our predict slide function here. We have accept 2 levels, level 1 and level 2, and we have getting the different patches from different levels, and using that for the prediction model.predict and get the prediction matrix. It's very similar. We didn't notice any form of difference. Finally, this notebook heat map accuracy is just evaluates the heat map produced by our model. So here are the necessary inputs and mounting. Here sets up the directories and passes. This is the confusion matrix plotting function. And here we load the heat map accuracy function, which accepts line name heat map suffix, which is just used to specify the location of the heat map file, and also heat map stride and threshold. And we get the heat map here, and also use it to compare with the ground truth mask to get the true positive, true negative, false positive, false negative, and calculate accuracy precision report. And we also return the heat map and mask here, so we can show them below, and also use them to compute the confusion matrix, and also using the plot confusion matrix function to get the figure as shown here. We have done this for 091, 075, 084, and it looks great. This should wrap up the whole presentation of our project. And here is our project folder. We have a lot of notebooks and also a lot of folders, data folders here. And thank you for listening. It's very enjoyable doing this project, and we have learned a lot. Thank you so much. Goodbye.